Sample problem 6.2. How much more energy per photon is there in green light that has a wavelength of 532 nanometers than in red light, which has a wavelength of 635 nanometers? So let's remind ourselves a little more detail about visible light. Visible light is made up of all the colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet, sometimes referred to as Roy G. Biv for all of those colors. Okay? The wavelength range for visible light is from somewhere around 4 times 10 to the minus 7 meters all the way up to about 7 times 10 to the minus 7 meters. Or, if you want to use the metric prefix nano, 10 to the minus 9, you get 400 nanometers up to 700 nanometers. That's, a little bit variable, and it probably depends on the individual, but somewhere in that range. It's difficult for most people to see colors beyond that range. So the 400 nanometers on the left is violet, and then the 700 nanometers on the right is red. And so all the other colors are in there. So orange, yellow, green, blue, and then indigo. Those are all the colors in between there. So for this particular problem, there's 2 colors that we're looking at. There's 2 wavelengths we're looking at. One wavelength is 532 nanometers, which is in the green range, and then 635 is in the red range. So those are the 2 different types of photons that we're looking at. Okay, so the energy of a photon is equal to h nu. However, if you recall from section 6.1, there is a relationship between wavelength and frequency for electromagnetic waves. The speed of light is equal to the wavelength times the frequency. So the frequency is equal to the speed divided by the wavelength. So we can substitute this in here and have h times c over lambda. And that is another way to calculate the energy of a photon based on its wavelength. Again, the assumption here is it's the speed of light. It must be operating in a vacuum or near vacuum conditions. Okay? So what we could do is we could do 2 separate calculations. We could calculate the energy of the photon that has 532 nanometers. And then we could calculate the energy of the photon that is at 635 nanometers. And then take the difference and call that delta E. Okay. Now, this would be hc over lambda, where lambda is 532, minus hc over 630, or lambda 635, right? Just substituting the equation for energy. And what you could do is you could be a little bit more clever, and you could factor out the hc and make this hc times 1 over lambda 532 minus 1 over lambda 635. That would work also. So you could do either of those 2 approaches. I'll go ahead and use this approach right here for this particular problem. Okay, so let's see if we have room over here. Let's try it. Okay, so the energy. Now, one thing that comes up is that because wavelengths are often reported in nanometers and not in meters, or MKS, CGS, or systems of units comes into play. So let me do the conversions here. 532 nanometers and 10 to the minus 9 meters is 1 nanometer. So what you end up with is 5.32 times 10 to the minus 7 meters. Now we're in the MKS system. And then the same is true for the 635. 635, 10 to the minus 9 meters per 1 nanometer. and that gives you 6.35 times 10 to the minus 7 meters. So those are our two wavelengths in meters. So let's do the energy of the photon that's at 532 nanometers. It would be hc over lambda, right? Now, the constants here are pretty large values, so let me just write it out here as equals 6.626 times 10 to the minus 34 joule seconds. So that's h. That's a constant. What value should I use? I'm going to go ahead and use 2.997 times 10 to the 8th meters per second for the speed. And then we're going to divide that by the wavelength, which is 5.32 times 10 to the minus 7 meters. Okay? So that's going to give us an energy for the 532 nanometer. And let's go ahead and calculate that one. Okay, so 6.626 times 10 to the minus 34, that's h, times 2.997 times 10 to the 8th, that's c. Oops, let's try that again. 6.626 E34 minus times 2.997 E8 equals. Okay, so that's not enjoying doing that. So we'll go ahead and use parentheses. 6.626 times 10 to the minus 34. There we go. Okay. So there's our HC. 6.626 times 10. Okay. Boy, this calculator. Let's try it again. I'm going to clear everything. Make sure we can get this right. 6.626 times 10 to the minus 34. Close parentheses. There we go. There's H. Times parentheses. 2.9979 times 10 to the 8th. Close parentheses. Equals. Wow. For some reason, this thing is really confusing. So let's use a different approach. What I'm going to do is I'm going to use my head a little bit. So 6.626 times 2.9979 divided by 5.32. And you get 3.73. So I'm going to come back over here. Now I'm going to do the powers of 10. We have 10 to the minus 34. And then we have 10 to the 8th. And then we're going to divide that by 10 to the minus 7. Okay? So when you multiply when you multiply powers of 10, you add the exponents. When you divide, you subtract the exponent. So this would be equal to 10 to the negative 34 plus 8, which is negative 26, minus a minus 7, right? So that's plus 7. So that's negative 26 plus 7, so that's negative 19. So our energy then for the 532 nanometer photon would be 3.73 times 10 to the minus 19. And then what are the units like? The meters cancel here and the seconds cancel here, and you got joules. Okay. So there's the first one. As I can see here, we're already running out of room. So now let's do the 635. Again, hc over lambda. So that would be 6.626 times 10 to the minus 34 joules seconds. That's h. Then we're going to multiply it by c. 2.9979 times 10 to the 8th meters per second. hc divided by lambda. 6.35 times 10 to the minus 7 meters. Okay? So now let's go ahead and do that calculation. hc over lambda. 6.626 times 2.9979 divided by 6.35. And you get 3.13. Now let's do the powers of 10. We have 10 to the minus 34 times 10 to the 8th over 10 to the minus 7, which are actually the same numbers we had in the previous problem, so we should get the same answer. So this would be 10 to the minus 26 over 10 to the minus 7. That would be 10 to the minus 26 times 10 to the plus 7. So that's 10 to the minus 19. Remember, when you're multiplying powers of 10, you add the exponents. Okay? Notice that it was minus 7 in the denominator. That's the same as multiplying by 10 to the plus 7 in the numerator. So times 10 to the minus 19. Again, the units come out to joules. Now, this is a small enough calculation. These numbers are small enough we can go ahead and do it here. The difference in energy between the two would be the energy of the 532 nanometer photon minus the energy of the 635 nanometer photon. So this would be 3.73 times 10 to the minus 19 joules minus 3.13 times 10 to the minus 19 joules. Well, guess what? They're both times 10 to the minus 19. That means we can directly subtract the decimal numbers. So 3.73 minus, let me get rid of that h. I don't want people to think that that's part of this answer. So 3.73 minus 0.13 is 0.6, right? Times 10 to the minus 19. Now, we can move this over one space to make it scientific notation. And that would make this smaller by 1, minus 20. And there you go. So the difference in energy between those two photons is 6.0 times 10 to the minus 20 joules, which is, a relatively small fraction of the energy of each photon. The photons themselves are around 3 times 10 to the minus 19 joules or so. So even our untrusty calculator, we're not going to let that get in the way of solving these problems.